Here are three limits and continuity problems. So determine the points of discontinuity and classify them. So you remember classifying them means, are they removable? That's just a hole. Are they jump discontinuities? That's you go along and then you move up. Are they infinite? Does one or both edge shoot off to infinity? Right? Or are they none of these? Or, as I like to say, ugly. Okay, so what is this? Well, the top is never going to be discontinuous. Plug in any number you want, it looks nice. The bottom is going to be discontinuous. Well, when is it going to be discontinuous? When it's equal to 0. So when is 1 minus x equal to 0? It's discontinuous at x equal to 1, right? Plug in a 1, it's undefined. The function is defined there, you know it's discontinuous. Well, let's think about what's actually happening here, okay? You can do this with a little table, probably that's the nicest way. We're looking at 1, so let's start at negative 1. Negative 1, we got negative 3 minus 3, the numerator is negative 6. The denominator is, let's see, 1 minus negative 1, that's 2. Absolute value of 2 is 2. So negative 6 over 2 is negative 2. At 0, let's see, we get negative 3 over 1. Oops, I did negative 6 over 2 and I got negative 3. I should get negative 3, right? Negative 3. Well, we happen to know that if you put in 1, it's undefined, but what if we're getting really close there? What if it's like 0.9? Can you see that if it's 0.9, what you have is you have like 2.7 minus 3. So that's minus 0.3 in the numerator. And then in the denominator, we have 1 minus 0.9. That's 0.1 in the denominator, that's minus 3. In other words, if you looked at the graph of this, okay, for everything left of 1, the value's negative 3. Negative 3, negative 3, negative 3, whoop, undefined there. What about to the right of there? Well, you can plug in 2. 2 gives you 6 minus 3, 3 on the top, 1 on the bottom. If you do 3, you can just double check, it's 3. This is what the graph looks like. And this is a jump, classic jump discontinuity. Okay? How about this right here? Well, notice the denominator is discontinuous at 2 points, 2 and negative 2. So discontinuous at t equals 2, t equals negative 2. You could do a little table, but you could also just remember what you know about rational functions. That's t minus 2, t plus 2, right? T minus 2 is a classic asymptote. The denominator is 0. The numerator isn't. So at 2, and you could graph this and you could see, essentially what we have here is zoop, right? And zoop. But the other issue is the point, let's see, I think this goes like that, something like that. The other point that's an issue, so what happens at 2, that's an infinite discontinuity. And I'm going fairly quickly here. You can ask me details about these problems, but hopefully you can see from the graph, one side is shooting off to infinity, one side is shooting off to a height of negative infinity. What happens at negative 2? Well, at negative 2, right, when you're really close to negative 2, these terms actually cancel. Plug in anything you want there, and it's the same as here, right? If you plug in negative 1.9 and negative 1.9, those two terms cancel. And so you get 1 over negative 1.9 minus 2. That's really close to 1/4, right? Let's see, where am I at here? But there's a hole there. So this is removable, right? It's removable because there's a hole. To the right and to the left of this, it looks just a whole lot like 1 over t minus 2. Okay, one last piece. Do you remember what tangent looks like? If you don't, you might go to Desmos and you might look at the graph. Okay, the graph has just a whole lot of vertical asymptotes. And where are they? They're at pi halves, pi 3 pi halves, 5 pi halves, and on for both directions. Every single one of those is an infinite discontinuity. So x equals, and what we do there is we write pi halves, that's the smallest, and then you're adding pi, adding another pi, so we put k pi for any integer k. And these are infinite discontinuities. I hope that's somewhat helpful.